What is the use of X-ray diffraction? Well, X-ray diffraction is used to obtain structural information about crystalline solids. It is also useful in biochemistry to solve 3D structures of different complex biomolecules. It also bridges the gaps between physics, chemistry, and biology. Let us always remember that X-ray diffraction is very important, especially in the fields of solid-state physics, biophysics, medical physics, chemistry, and biochemistry.
And now let's talk about the history of X-ray diffraction. On November 18, 1995, Wilhelm Conrad Roentgen accidentally discovered an image cast from his cathode ray generator, projected far beyond the possible range of the cathode ray known as an electron beam. The first of scatter process to be recognized was discovered by Max von Laue, who awarded the Nobel Prize in Physics in 1914. He showed that if a beam of X-ray passed through a crystal, diffraction would take place at the right angle to the direction of the rays. The discovery provided a new method for investigating the fine structure of matter. After a few months, in 1915, English physicist Sir William Henry Bragg showed that diffraction pattern can be used to determine relative positions of atoms within a single crystal. On February 28, 1953, in Cambridge University, scientists James D. Watson and Francis Crick announced that they have determined the double helix structure of DNA, the molecule containing human genes. The molecular biologists were aided significantly by the work of another DNA researcher, which is Rosalind Franklin. Although she is not included in the announcement, nor did she share the subsequent Nobel Prize award for it. And lastly, in today's generation, the diffraction improved by computer technology or methods used to determine atomic structure and in medical application.
Today, we will going to tackle about how X-ray diffraction works. X-ray diffraction works through wave interacting with a single particle, wave interaction with a solid, and it works through crystalline materials. X-ray diffraction may works through wave interaction with single particles because incident beams are scattered uniformly in all directions. Diffraction works also through wave interacting with a solid because scattered beams interfere constructively in some directions, producing diffracted beams. And random arrangements cause beams to randomly interfere and no distinctive pattern is produced. Crystalline materials. Diffraction works through crystalline materials because regular pattern of crystalline atoms produces regular diffraction pattern. Diffraction patterns gives information on crystal structure. According to Bragg's law, X-ray diffraction works through similar principle to multiple slit experiments. Constructive and destructive interference pattern depend on lattice spacing and wavelengths of radiation. And also, it's true by varying wavelength and observing diffraction patterns, information about lattice spacing is obtained. X-ray diffraction schematic or diagram. The pictures or diagrams demonstrate that, as we can observe in array A versus array B, dots in A are closer together than in B. Diffraction pattern has a spots farther apart than pattern B. Array E, hexagonal arrangement. Array F, pattern created from word nano written repeatedly, and it is any repeating arrangement produces a characteristic diffraction pattern. In array G versus array H, we can observe G represents one line of the chains of atoms of DNA or single helix. Array H represents the double helix, distinct patterns for single and double helices.
This time, we will be analyzing diffraction patterns. Diffraction is defined as the bending of waves around the corners of an obstacle. In analyzing diffraction patterns, we need to look for the variables present: the distance, diffraction angle, the number of maxim, and the wavelength. Based on the data is taken from a full range of angles, specifically the diffraction angles. For simple crystal structure, diffraction patterns are easily recognizable. Why? Because of the structure of the crystal. For the phase problem, only intensifies of diffracted beams are measured, so it means we are no longer have to measure the refractive beams because they are not included in this process. Phase info is lost and must be inferred from data, so time by time we'll be measuring diffracted beams based on our data. For complicated structures, diffraction patterns at each angle can be used to produce a 3D electron density map. This is the illustration of the 3D electron density map. Based on the data below, the top right image depicts a 3D electron density map. So this one, the right one. The known variables are the distance, the wavelength, and diffraction rate of our diffracted beams. So the distance 1 has 1.554 rather A, and the distance 2 has 1.09 A. The wavelength has 0.6975 A, and the diffraction rate is 20 C. The intensity counts higher in between the scale of 20 to 30. So the scales decreases as the distance advances.
Solving the structure of DNA. History. Rosalind Franklin, physical chemist and X-ray crystallographer, who first crystallized and photographed BDNA. Maurice Wilkins, collaborator of Franklin. Watson and Crick, chemists who combined the information from Photo 51 with molecular modeling to solve the structure of DNA in 1952. Photo 51 analysis. X pattern characteristic from helix. Diamond shapes indicates long extended molecules. Smear spacing reveals distance between repeating structure. Missing smears indicate interference from second helix. Information gained from Photo 51, double helix, radius 10 angstroms, distance between bases 3.4 angstroms, distance per turn 34 angstroms, combining data with other information, DNA from sugar, phosphates, 4 nucleotides, C, A, G, and T. Chargaff's rules: A equals T, G equals C. This is the molecular modeling.
Let us proceed with the applications. X-ray diffraction can be used in finding the structure to determine the functions of proteins. It can also be used in distinguishing between different crystal structures with identical compositions. Also, it can be used to study crystal deformation and stress properties, and also rapid biological and chemical processes, and much more. Take for example the sample problem. You direct a beam of 0.154 nanometer X-rays at certain planes of silicon crystal. As you increase the angle of incidence of the beam from 0, the first strong interference maximum occurs when the beam makes an angle of 0.5 degrees with the planes. A. How far apart are planes? B. Will you find reference maxima from these planes at greater angles of incidence? To answer this problem, let us first identify and set up. This problem involves Bragg reflection of X-rays from the planes of a crystal. Bragg reflection is also called Bragg condition in honor of Sir William Bragg and his son Lawrence Bragg, the two of X-ray analysis. This Bragg reflection was proposed in response to their discovery of surprising patterns of reflected X-rays. William Bragg and his son found out that these crystals at a certain specific wavelengths and incident angles produce dense peaks of reflected radiation. Bragg reflection or Bragg condition has the formula of 2 times d, or the distance between adjacent angles, then the sine theta is equal to m, or the interference maxima, times the wavelength. With m have different values, it can be 1, 2, 3, and so on. So in part A, we use the Bragg condition to find the distance d between adjacent planes from the known wavelength, which is equal to 0.154 nanometer, and the angle of incidence, which is equal to 34.5 degrees, and for the interference maximum, which is 1. So to execute, we have here, we are going to use the formula for Bragg condition, going to transform the formula earlier. So we have this d is equal to m, or the interference maxima, times the wavelength, or this inverted y, over 2 times sine theta. So substitute all the values. We have m is equal to 1, wavelength is equal to 0.154 nanometers, then 2 sine, the angle of incidence is 34.5 degrees. So we have here 0.136 nanometers. Now for letter B, to find the values of theta, or the angle of incidence for interference maxima corresponding to other values, we are going to use the formula again. We are going to transform the formula earlier from the Bragg condition, or the Bragg reflection formula. So we have here, to calculate other angles, we solve for sine theta. Sine theta is equal to m, or the interference maxima, times the wavelength over 2 times d, or the distance between adjacent planes. So we have here m is equal to m 0.154 nanometers over 2 times the distance 0.136 nanometers. So we have here m times 0.566. Let us evaluate. Our result in part B shows that there would be a second interference maximum if the quantity 2 wavelength over 2 distance between adjacent planes is equal to wavelength over distance between adjacent planes were less than 1. This would be the case if the wavelength of the X-rays were less than d, which is equal to 0.136 nanometers. To answer the questions from A, how far apart are the planes? The planes are apart within the distance of 0.136 nanometers. Then B, will you find other interference maxima from these planes at greater angles of incidence? The answer is yes. Let us summarize it all. Therefore, X-ray diffraction is a technique for analyzing structures of biological molecules. X-ray beam hits a crystal, scattering the beam in a manner characterized by the atomic structure. Then, even complex structures can be analyzed by X-ray diffraction, such as DNA and proteins. Thus, it will be useful in the future for combining knowledge from physics, chemistry, and biology.